Hello everyone. Here we discuss about the hardware type of energy management based series inverter configuration of shunt active power filter. Before going to hardware prototype, we can discuss about the basic circuit configuration. All we know that recent developments and smart management increasing the non-linear loads in the network, which causing the pollution of the grid power. So here in the circuit, the nonlinear load is mimicked by the diode bridge rectifier and it connect directly to the grid. Here nonlinear load will draw the current from the grid which is nonlinear in shape. So it will increase the percentile THD of the current. To compensate this, series inverter based shunt active filter is connected in parallel with the nonlinear load. The shunt active filter will compensate the harmonics drawn by the load and also inject the active power from the and also inject the active power which is available in the sources. Here in series inverter we using the two sources. One is the solar panel and another is the battery. The main advantage of the series inverter configuration is requirement of the DC link voltage is half of the single three-phase inverter configuration. Coming to its operation, both inverters will switch such that it can compensate the harmonics whichever drawn by the non-linear load and also inject the active power and also control individually. This inverter control independent with respect to this inverter. Generally, non-linear load draw the power from the grids. It causes the disturb the current shape and also increase the THD as we discussed. So series inverter will inject the harmonics and compensate the grid current and it maintain the percentile THD which is drawn from the grid. And also it inject the power which is available in the sources depending on its configuration divided into two different conditions. One is the available power at the sources is lesser than the load requirement power and one second is available power is higher than the load requirement power. And this conditions is divided into number of modes. We can discuss in the next slide. So in this slide, the modes of operations are discussed and also discuss the status of the sources and load status and inverter status and grid status. Here, here the mainly grid status will be changes depending on the available power of the sources. So if available power is lesser than the load power, grid will inject the extra remaining power. Otherwise, if available power is higher than the load power, grid will take the remaining extra active power into it. Here mainly the indications, first green and up arrow indicates which means that they are supplying the power and yellow down arrow indicates they are taking the consuming the power that's supplied by the sources and light blue black line indicates that they are not operating and not supporting that power. Coming to mode 1 operation, the nonlinear load is presented in mode 1 operation. The nonlinear load is presented and there is a two conditions. If available power is lesser than the load power, available power is greater than the load power. So if available power is lesser than the load power, the grid is supplying the extra remaining power required by the load. If available power is higher than the load power, grid is taking the active power from the sources. In mode 1 operation, both inverters will inject the same active power and depending on the given reference. Solar inverter operating with the MPPT algorithm and it giving the current reference which is available at the solar power, and the same reference also we given to battery inverter, so such that the both inverter can switch and inject the according to reference power. So coming to mode 2 operation, there is no nonlinear load. Here there is no requirement of harmonics. In mode 1 operation, there is a nonlinear load is presented, it drawing the harmonics. So those harmonics compensated by the sources, both inverters. And in mode 2 operation, there is no nonlinear load presented. Whatever the available power, both are injected into the grid. You can see there is no light blue and black line indicates it the load status and active power status from the grid. It is showing the sync status, and both sources are injecting the power. Similarly, in power is available power is more than load power, condition also same. In coming to mode 3 operation, the same as to mode 1 operation, the load is presented, but in this case the available power at the battery is reduced. The percentage is also reduced to 30%. Consider the 30%. The battery, it cannot inject the active power. So this battery inverter we are using for the to compensate only harmonics. And whatever the requirement of the load power will be injected using the solar inverter. So you can see here the active power status is shown as the not operating condition in the mode 3 operation, but it is compensating the harmonics. But solar inverter is compensating the harmonics along with the injecting the active power. Here the main keynote point is that we need to control both inverters in the individually. First inverter, it inject the active power and along with the harmonics, and the second inverter only give the harmonics. So in series inverter the current is same, but here the inverter, second inverter seen by the current is only harmonic current reference, so such that both can control independently and supply to the load and grid. If the similarly, if available power is more, then it will inject it into the grid. In mode 4 operation, similar to mode 2 and mode 3, there is no battery power is available, and whatever the available power at the solar will inject it into the grid. These modes of operations will verify by developing the control circuit using the MATLAB. So hi everyone. So this is the MATLAB simulation configuration for series inverter configuration for energy management between the two inverters using the two sources like solar as a one source and battery emulator as a another source. First we can discuss about the first source, solar emulator, which is connected to the first inverter of the series inverter. So this is the solar emulator, and we operating through the solar emulator software. We set the open circuit voltage is 256 and VMPP is 200 volt. And solar emulator ratings are the 15 kilowatt rating, and it is 1500 volt, 1000 volt, 15 ampere current. And this can be operated by using the solar emulator software. Here we can easily mimic the solar panel characteristics using this software. So that's why we can use solar emulator in 24 hours anytime. We can mimic the solar panel characteristics, and you can see that this is the IV characteristics and PV characteristics. Depending on the setting of the irradiance, the IV and PV characteristics will vary. Okay, start. Next we are going to battery emulator as we using as a second source for the series inverter configuration. This battery emulator can operate as a source and sink. We can operate in both conditions. So this battery emulator ratings are the 15 kilowatt plus or minus 30 ampere, and battery emulator can operate using the battery simulator software, which can be shown here. So this battery emulator software we can mimic any type of batteries like a lead acid, nickel cadmium, lithium ion, nickel metal hybrid. So suppose we selecting the lithium ion, and we can select the number of cells, how many cells we can use in the pack, and state of charge of the battery, and each cell voltage, and internal resistance whatever required for the lithium ion. Suppose I am taking the 0.01, and rating of the battery I am using the 4Ah and cutoff voltage 10,
and we can directly go to bat simulation. So here in this place it will show the battery characteristic like voltage versus SOC. So we chosen the battery state of charge is 80%, so the curve is showing the 80% over here, and this can mimic the battery characteristics of the battery. This battery emulator we can mimic the battery characteristics. Now we can see the series inverter configuration of shunt active filter. So these two are the two inverters we connected seriously using the isolation transformer. This is the first inverter of series inverter, and this is the second inverter. First inverter input source is connected to the solar emulator, and second inverter input source is connected to the battery emulator, and output of these two inverters are connected seriously using this isolation transformer. This is the isolation transformer. Output of this isolation transformer connected to the grid using through filter inductance. So in this network generally there is also loads are presented. These are the loads we using in this network. This is the single phase load, and this is the three phase load. This single phase load is connected to the nonlinear load, nonlinear network. This is the rectifier circuit. Output of this rectifier circuit is connected to the single phase load. And to operate this type of circuits, we want to integrate with the grid, and we need to inject the harmonic active power and harmonic compensation. We need to operate this in the closed loop operation. So to operate closed loop operation, we require the sensing circuits. So these are the sensing circuits. These are the voltage sensors, and these are the current sensors, and there is also current sensors. So this is the inverter output current sensors, and that is the load current sensors to sense the harmonic quantity from the in the load. And this sensing data is collected by the DSP controller board, and this is the DSP board F28790. This using ADC pins, we taken this data into the MATLAB simulation. And also this is the DC link voltage sensors. These two are the we need to operate the solar emulator in maximum power point region, and these are the auxiliary supplies for the control sensing circuits. And also we using the power quality analyzer to measure the quality of the power of the grid. We using this power quality fluke power quality analyzer. We can measure the THD of the percentile THD of the current here. And this is the DSO here. This DSO, we can see the waveforms of the inverter current and load current and grid current. And these are the current sensors to check the waveforms of the load and grid and inverters, which is directly connected to this DSO. Now we can go to the mode 1 operation of series inverter configuration of shunt active filter. So this is the control logic of mode 1 operation. This control logic is dumped into the DSP controller board, and this DSP controller generated the switching pulses to the both inverters, and this both inverters are switched depending upon the control logic generated reference. So this control logic is not generating the pulses because we not connected turn on the pulses to the inverter, and before turning on the pulses the available nonlinear load is drawing the power from the grid, which is non-sinusoidal in nature. So you can see the current shape of the nonlinear load, and this the grid current shape. So it is same as the nonlinear load. So this is the non-sinusoidal, which is having the some harmonic content in this. So the total harmonic distortion of this grid current is around 24%. In this mode 1 operation, both inverters control logic is given the same reference, and this reference are generated by the solar emulator maximum power point current reference, and both inverters are controlled by the same reference, and both injected the same power. And if we turn on the pulses to the inverters and we start compensating the harmonics from the grid. So here the available power of the sources is same as the load power, so the injected grid current is 0, and the total power coming from the sources and which is given to the load. So here you can see the maximum power point operating region is achieved. So if you change the irradiance from 20% to 50%, the red point start tracking the new maximum power point with of PV characteristics and reaches the maximum point. And you can see the solar emulator injected power is around 580 watt. And also you can see the available power from the sources is more than the load power, so the extra power is injected directly to the grid. You can see the shape of the grid current is sinusoidal, and this is the non-linear load, and you can see the THD of the grid current is 7%. And if we increasing the reference from irradiance changing from the 50% to 75%, again it starts tracking the new maximum power point reference, and you can see the current shape. Extra power start injected in, extra power is also injected into the grid. The non-linear load current is not changing, so the whatever the extra available power from the series inverter side is directly injected into the grid. You can see the THD further decreased to 4%. It is lesser than the 5%. And also the battery emulator, second inverter battery emulator is given also triggered with the same reference which is given to the first inverter. So it start also injecting the power which is same as the 800 watt, and there also 800 watt. So you can see the characteristics of the voltage versus SOC. It starts discharging the from 50%. You can see here it is around, it is 46%, it decreasing. You can see the power around 800 watt. Also you can see the power of the solar emulator is 880 watt. So this is the mode 1 operation. In mode 2 operation there is no non-linear load is presented, which means non-linear load current is totally 0. So whatever the available power at the source is directly injected into the grid. Because there is no non-linear load, there is no need required of harmonic compensation. So now we turning up the non-linear load. You can see the current of the non-linear load is totally 0. Whatever the available power at the inverters directly injecting into the grid. So now you can see the THD of the current, it is around 2.4%. And here you can see the power is not changed anything. It is 880 watt, and grid battery emulator power also same as 880 watt. These two are the mode 1 and mode 2 operation of the series inverter configurations. Now next we can go to mode 3 operation and mode 4 operation. Now we can go to mode 3 mode 4 operation. So this is the mode 3 mode 4 operation of control logic, control circuit of MATLAB simulation. So this MATLAB simulation control logic will dump into the DSP board. This DSP board switch the two inverters with the switching pulses, and those two inverters are switched depending on the control logic generated reference signal. So here the in mode 3 mode 4 operation, as we discussed in the basic circuit configuration, the battery emulator available power is less, and the percentage SOC is it is around 30%. So this battery emulator, it won't supply any active power, it only support the harmonics, and whatever the active power injection into the grid or load is done by the solar emulator. So whatever the available power at the solar inverter, first inverter source, so it will be injected into the grid and load. So this is the non-linear load drawn power from the grid. So the shape of the current is non-sinusoidal, so as seen in the first mode and mode 1 and mode 2 operation. So now we turn on the pulses to both inverters. You can see the current shape is changed to sinusoidal, and the harmonics are compensating from the inverter. So the available power at the sources is lesser than the load power, so the total load power, so the remaining power is supplied by the grid to the load. Now we change the irradiance. Here you can see the battery, it not giving any active power, it only compensating the harmonics. Now if we inject the active power from the solar inverter, so by changing the irradiance, now I am changing 5% to 75%. So it start tracking the new MPP point PV curve. You can see the red point, it is moving to the top. You can see this curve, inverter power is more than the load power, so it start injecting into the grid. You also see the battery, whatever the extra power available at the inverter, it starts injecting into the grid. Battery starts charging. You can see the battery start charging, its SOC is increasing from 30% to 35%. So this is the main advantage in the mode 3 operation. We can control the we can inject the total power from the first inverter, and if there is no any power, we can charge the battery using the mode 3 operation. If we turn off the non-linear load, so the non-linear load current is totally become zero. Whatever the available power at the grid sources, it will directly inject into the grid. You can see we turn off the non-linear load current, it's totally become zero. Whatever the available power at the sources, it will start injecting into the grid. You can see that THD of the current, it is around 5%. And in this condition also the batteries will charge the available power at the first inverter and grid. It will start the charging the battery. You can see the current going into the battery, it is minus 0.25. It start charging, it is increasing from 30% to 44%. So now we turn on the pulse non-linear load, automatically start inject whatever the power required by the load, it will be injected into the load, and whatever the extra power it is there, it will inject into the grid. And now if you change the power irradiance from 75% to 100%, the power extra power is injected into the grid. If you turn off the non-linear load, so whatever the extra power is go to the grid. These are the mode 3 and mode 4 operations of the series inverter configuration.